During the pandemic, it really helped me a lot to be connected through this wonderful seminar series. I really enjoyed, for example, the internal combustion engine series that we had 3 years ago with Professor Rolf Races giving a talk. I think there was Kelly Senegal who was giving a talk about internal combustion engine future and all. And also Professor Hua Zhao giving out a really wonderful talk about the futuristic internal combustion engine technology that's being researched. So it's in line with it. It's revisiting some of those topics that's more specific to the research that's done at the University of New South Wales here in Sydney, Australia. And then also my throw out of message to the field that there are many exciting keywords that you can enjoy to further develop or completely redevelop the internal combustion engine for future application. So I picked up 3 topics, keywords, like I mentioned. And the first keyword is high-tumble, that would be rooted for petrol engine, gasoline engine in your term. For those of you who are not familiar with the British. So high-tumble applicable for petrol engine, energy assistant that's used for diesel engine in operation with low reactivity fuel, and I'll get to that point later on. And pretty big word, buzzword, hydrogen. So I do face this, and I think you will agree with me that in policymakers' mind, internal combustion engine is pretty much dead. Their impression about the current internal combustion engine is like this, that it's just a junk metal that has no future in it. And in comparison to that, they would think that, okay, the electric drive with shining color, that would be the future. So that's how the policymaker's mind is set for it. But in reality, if you are an engineer or a scientist who are really knowledgeable of advanced engine technology of today, the new engine is looking just like the new electric drive. It's just shining like silver. It's a new, purely advanced, many high-tech, all implemented in this lovely machine. So I like to suggest to do a quick reality check before I go into some of the technical details that I've prepared. The reality is that people are still buying internal combustion engine vehicle, and they will buy internal combustion vehicle in any foreseeable future. The market analysis is actually saying that even towards 2027, there will be annual growth of market, internal combustion engine market that's exceeding 8% annually. Bringing this kind of number to the investors, they will just jump off and then try to bring in any money that they have into. So this is a still exciting and growing market that everyone can enjoy. The growth would be definitely around Asian countries, Australia, and Middle East. But even in the US, there are still many buyers rooting towards the internal combustion engine vehicle. Of course, there are an increasing number of people who would be interested in electric vehicles as their next car. But equally, when it comes down to real deal to buy next vehicle purchase, then it actually comes down to internal combustion engine. That's how the market analysis and the survey is suggesting. The policymakers' efforts to completely phase out internal combustion engine in European countries has failed. It is more or less that the experts' voice finally was heard. There are a lot of factors around it, but in the end, it is internal combustion engine that has a longer-term value. So having, say, carbon neutral fuel, the fuel is generated using CO2 so that the emitted CO2 from vehicle is actually considered as a zero towards the CO2 contribution to the environment is carbon neutral fuel. As far as a synthetic fuel, like carbon neutral fuel is used in internal combustion engine, that internal combustion will be considered as the next generation technology too, even in the European countries. How about the industry? So you will hear a lot of news from industry and the media that well, investors meeting and media release will say, hey, we'll phase out internal combustion engine, no more internal combustion engine vehicle. normal development or investment into internal combustion engine. Well, if you do an actual quick reality check of it, major automakers are all actually committed to further invest into internal combustion engine. Toyota is highly committed to maintain their internal combustion engine technology development. Hyundai is a part of it. BMW has never even mentioned about phasing out their internal combustion engine at all. Porsche is really aggressive in bringing in that carbon neutral fuel technology into reality. Renault and Ferrari, all these manufacturers are all with that. Some manufacturers actually claim that they're gonna kill internal combustion engine pretty much. General Motors is leading it, such as well as Volkswagen. But General Motors is beyond the curtain investing into internal combustion engine manufacturing, like a $1 billion. Oops. And the Honda is correcting themselves that they claim that they're going to phase out internal combustion engine pretty quickly by 2035, for example. But then they are now changing their words that we will actually work on internal combustion engine even beyond 2040. So for scientists, engineers, we are not the one who would be dragged and pulled by policymakers' message or industry, but we are the one who would actually deliver a message to the policymakers and to the people, as well as manufacturers. That's my stance here. So what do? We then wanted to develop new technology that can be prepared for future. And if we have internal combustion engine technology that can be part of the future of mobility, definitely it will be heard. And I think I saw some question around it, and I don't mind to take those on board during the seminar. There's a question about the success of comments. I don't know what exactly that means, but if you specify the question again, then I'll be to take on the question. And like I said, if you type in the question, I'm pretty sure I can read it out and address the question during the seminar, or Professor Taegan Fang can.
It's better to answer them at the end, so we can.
Oh, okay. Yeah,
that's thank you.
That's also a good option. So I'll give you out the talk briefly, and then later try to address the questions live. And even after the webinar, please type in use the comment section to ask further questions, or try to reach me out. I'll be happy to address any questions. So at the University of New South Wales, we're working on 5 main themes at the moment. One would be very consistent with many others' research: super lean burn. So gasoline engine that's running on lean homogeneous or lean stratified mixture for significantly improved fuel economy. And that is working really well with the hybrid operation too. So when gasoline engine is electrified together with electric drive, then it will achieve massively improved fuel economy and CO2 reduction in return. The second theme that we are very active at the moment is this flow and turbulence measurement, and towards further improved efficiency of gasoline engine. There are a lot of things that need to be done, that need to be researched regarding the petrol engine flow and turbulence, which means there is a potential for further improvement regarding the fuel economy as well as the CO2 reduction. And when it comes down to diesel engine is so ubiquitous. It's versatile for a range of applications. And one area that we're working on actively is a diesel engine used in unmanned aerial vehicle that is compact, durable, and powerful, and can take up the long range operation, especially when the fuel type is very different to conventional diesel. How we address that combustion condition is one main problem that we are addressing at the moment. And of course, a lot of people are interested in hydrogen. We were lucky enough to step into this hydrogen area a few years back, say 2017, 18. There was a high interest on utilizing existing infrastructure by retrofitting some of the diesel engines. So we took up that research topic and have produced some exciting outcome. So we'll introduce that to you today. And there's very long-term research that I will continue no matter what. It's fundamental research It's actually welcomed by the Combustion Institute in many ways. We look into the carbon particle structure in a very exciting way, that you expose some of the sampling probe right into the reacting flame. Within, there are many soot particles forming, and we're changing the sampling timing and duration and all the parameters to look into the soot particle evolution, structural evolution during the combustion. It's been applied for both diesel engine as well as petrol engine operations, gasoline engine operations, and keep producing some exciting new papers out of this research area. For a given time and for its timeliness, I prepared this flow diagnostics in a petrol engine as a one topic, and energy assist ignition in a diesel engine as a second topic, and hydrogen in a diesel engine as a dual fuel combustion mode as a third topic. So there we go. So the high-tumble gasoline engine is one technology that can be adopted into electrified powertrain in a very effective manner. So, for example, Nissan, or also the Ford, would say that here is BMEP, brake main effective pressure. So it's a power output. It's a normalized power output, the work divided by displacement volume. So power output over to the engine speed map will say that we will have operating condition that could be covered by electric drive. All these troublesome operating regions that can be covered by electric drive, such as low and high torque region, that engine speed is low, but then drivers get to press on the accelerator pedal aggressively, maybe to take over other cars or go uphill in a slow speed. When that happens, then that's where fuel economy is really struggling, or the power output generation is really struggling. That can be covered, boosted by having the electric motor. So internal combustion engine can get a nice assistance from the electric motor in that area. Just another example is low speed. When it's running at low speed, the fuel economy is actually awful in an internal combustion engine. So that can be assisted by electric motor. When that happens, then it's the role that's left for internal combustion engine is what's called a high efficiency operation range within the mid power output and the mid engine speed range. That's left as an excellent operation mode for the internal combustion engine. For internal combustion engine, that's the region where high efficiency can be maintained without worrying about all other troublesome operation zones in this BMEP and engine speed map. So for that high efficiency engine operation, the high-tumble is the key. So let's run a very quick and brief fluid mechanics lecture here. So what's turbulence in an engine? Intake airflow that is going into the cylinder, air is supplied into the cylinder, contains a lot of turbulence. It is in the first place very turbulent flow. The flow is going in, but then unfortunately the turbulence will decay very quickly. And by the time that you want to utilize it, like near to the top dead center where the spark is applied, the flame propagation happens, you wouldn't have much turbulence left. Because of that, we design the flow in a way that the intake flow has very well-defined structure. And so that can carry this high turbulent energy within. So we are actually encapsulating the high turbulence within the well-defined flow so that can be carried all the way to the near TDC region. And once the piston reaches to the near TDC, then the space is limited and the flow has no other ways to go. So start to break down. Specifically in a typical Pent-roof type petrol engine, SI engine, combustion chamber, the initial intake flow structure is more or less tumbling. So the intake port passage and the combustion chamber is designed to create that well-defined flow structure, bulk flow structure called the tumble flow. And near TDC, it has nowhere to go other than being broken down while the tumble flow is switch over into swirling motion, so swirl flow. So during that flow breakup, then we tend to generate high level of turbulence so that we can utilize that near top dead center. just brief fluid mechanics and why with high tumble flow can be utilized for high turbulence and in the end the high efficiency petrol engine. For that purpose, we've designed the diagnostic method. That's the where our excitement is, that we maintain the existing 4-cylinder conventional high tumble petrol engine as it is, while we added just 2 holes, one for the camera endoscope and the other for the laser endoscope. Well, specifically, it's a rigid endoscope, so it's a borescope. So we have 2 borescopes mounted and one to the side where the laser beam can go into so that illuminate whatever is happening within the cylinder. And the camera that's normal to the angle of the laser beam so that we can actually get 2-dimensional view of the flow field, just like the cross-sectional view of the Pent-roof combustion chamber. And of course, there are solid particles, specifically that's a 10 micron in diameter hollow glass particles flowing into the intake manifold and distributed nicely and flow into the intake port. The flow is going into the combustion chamber and we are actually visualizing it. The result example is shown here. This is Pent-roof shape. Piston is right there. The bright illuminated light is where the laser is hitting on the piston top surface. We have particles flowing in together with in-cylinder flow, tumbling motion, and we're capturing the particle motion and running the PIV algorithm, primarily implementing multipass fast Fourier transform, and then get the vectors extracted out and applying spatial filtering so that for each individual cycle, we can get bulk flow magnitude, bulk flow vectors, as well as turbulence. And if you repeat this for over 100 cycles, then we start to get an opportunity to ensemble average these individual cycles to get such a well-defined flow structure from averaged view of the vectors, and can extract now quantitative information such as flow velocity magnitude and how that changes over to varied crank angles, and extract the turbulence and how much of this turbulence energy is changing along the crank angle and all. So jumping into some of the example case, the intake flow is showing as the particles are flowing into the cylinder as we seeded it, and as those are illuminated by the laser beam. In this particular case, that the laser beam is illuminating the center line of the combustion chamber, and towards the end of the compression stroke, we get to see such a well-defined tumbling motion of the flow. As we are extracting flow vectors, you can see that, okay, there are many flow vectors during the intake flow, and gradually it's showing it's such a well-defined direction of the flow during the intake stroke, which settles down as the piston is far down there and start to move up to push up the flow. And then you start to redefining the flow structure, such as just like a tumbling motion. So the counterclockwise rotation is clearly visible in this measured flow field. And later, when the piston is reaching up to the TDC position, then we start to see the very interesting flow structure that could be captured near TDC, just like this. So this is now more focused on near TDC view. The flow is moving upwards and tilted to the top left corner simply because of the tumbling motion of the flow within the field of view. And near TDC, we start to see this interesting switch over of the flow structure. Up until here, there is a tumble with a center around here. And then we start to see the flow that's flowing from the left to right. In this case, exhaust valves to the intake valve side, interestingly. So the overall flow structure is that the flow is going upwards, tilted towards exhaust valve side as it is tumbling motion, tumble flow. It is how it was designed from the intake port passage design as well as combustion chamber. And near to the TDC, then we start to see the flow structure that is turning into very interesting and a complex flow component that has one small vector that's a remnant, the leftover of the tumbling flow. So one vortex that's remaining, while there's also still remaining flow that's coming upwards as if it was the result of the late compression stroke tumble motion. And the new flow that's generated, just like as it was illustrated with this yellow arrow, the flow direction is direct opposite to the upcoming tumble flow. And it is actually stronger than the remaining little tumble vortex. And so we redefined it as the bounce back flow, because this is a result of initial earlier the tumble flow that's coming up, hitting on the exhaust valve side and coming back towards intake. So as high tumble design was achieved in an engine, near TDC unexpected behavior or new flow structure actually emerges, just like that. The tumble flow disappears completely, and the leftover is the flow that's actually flowing from exhaust to the intake side. And what's the implication of this new flow structure? We try to compare that to the flow structure that's well-defined and well-known from the default intake valve closure setting. So the example case that I showed you earlier was a result of our intentional setting of advanced intake valve closure. So intake valve closes earlier, meaning that there are a lot of momentum left to maintain this tumbling motion and the flow intensity. When we do that, as you showed you earlier, we have flow that's going up, hitting on the exhaust side and coming back. So there is almost a horizontal flow towards the intake valve side as a leftover. When we then control the intake valve while setting it at default mode, meaning that it's set at a later timing, just like for the Atkinson cycle operation or Miller cycle, if there was a supercharger, which is not the case in here. But when you set the intake timing, intake valve closure timing late, then ultimately it's giving you the flow momentum loss. Some of them actually is lost back to the intake valves, and the leftover is a smaller. And in thermodynamics, that will give you effectively shortened compression strokes. So the thermodynamic efficiency will increase. But for flow intensity perspective, it's reducing the leftover momentum near top dead center. So the one that I showed you earlier, the flow that's hitting on the exhaust valve side and coming back due to this massive momentum doesn't really happen. It only settles down and becoming quiet as it's maintaining its own original flow direction, which is intake to the exhaust, just like in the original tumble flow direction. So what would happen to then the flame and spark stretch when the flow direction is completely opposite just by changing the controlling the intake valve closure timing? We actually run the flame imaging in the actual multi-cylinder engine dynamometer, doing the same endoscopic flame imaging at an extremely high speed. So we get to get a high strength spark stretch signal, that's a spark plasma, and also the natural combustion luminosity. It's a flame image, line of sight integrated, of course, quickly captured. And we realized that the spark stretch is actually following the flow direction immediately. The late intake valve closure, the flow direction was actually towards the exhaust side. So the spark stretch is actually to that end. And the advanced intake valve closure is giving out a spark stretch direction more towards the intake. So, and statistically, if we run a 100 cycle operations, or even it is just simply consistent with the flow direction. And as a result, the flame direction is also directly influenced by that flow direction. When you have flow that's going towards the exhaust intake side, then the flame is more skewed towards intake side. The flow, if the intake valve closure timing is set at default, so it's later than the advanced timing, then the flow direction is more towards the exhaust, and then the following flame direction is more skewed towards the exhaust side. This is a very interesting scientific finding because it has a direct impact on engine design and operating condition setting. So many engine manufacturers will be super surprised that, okay, by just changing the intake valve timing, we can end up having flame actually going towards the exhaust side, where the surface temperature is much higher than the intake side. So that operating condition might end up having higher knocking condition due to the high temperature exposure of the flame to more towards the high temperature surface on the exhaust side. So lots of key information that we could have obtained from the exciting new diagnostics that's called the endoscopic high-speed PIV. Then we've been lucky to enjoy this close collaboration with recent close collaboration with the Hyundai Motor Company, who has provided us a range of intake port designs, piston designs, different operating regimes and all. We've developed a significant database to check on how this flow structure changes and how turbulence distribution changes due to the change of intake port direction, its angle, the shape, and the piston and all. So there are more published papers will be produced out of this exciting diagnostics in the future. Okay, the second topic that I'd like to bring up is energy assistance, and it will be actually very brief because it's in an early stage of research for us. The idea here and the demand here is that if you're going to use a diesel engine in the unmanned aerial vehicle, those machines come with they demand the operation of an engine with very low reactivity fuel, because the fuels are produced from everywhere. So the quality of fuel is not guaranteed, meaning that the cetane number might be much lower than the conventional diesel fuel to which the diesel engine is optimized for. When that kind of condition is given, what do we do? How do we ensure that the ignition is reliable, repeatable, and combustion is strong enough to operate this diesel engine? So we've set up the optically accessible single-cylinder diesel engine that we have in the laboratory to operate what's called the ignition assistance system. It's very similar to diesel glow plug, if you're familiar with it, that the heat energy is supplied into the combustion chamber right at the beginning of the ignition of the mixtures. So you get to have, in addition to the auto ignition, you get to have additional ignition source. But there are a lot of questions actually left to here, that whether the presence of this high temperature solid body, does it act as the surface ignition source right at the surface of this electric rod, or would it just increase the overall environment, the temperature of the in-cylinder gas, and shorten the ignition delay? How does it impact the combustion if this ignition system plug is running even during the combustion event? All these questions were actually addressed by applying our new diagnostics called the flame image velocimetry. So as opposed to PIV, where we use particles to track the motion of the in-cylinder flow, we run an imaging at an extremely high speed and extremely high resolution to track the variation of this flame contrast. Because the signal is returning high contrast variation in a fine scale, very fine scale, because the flame temperature changes within and returning extremely small scale flame pattern change that's happening at a very short period of time. So we use that interval as if that's some sort of a tracking medium that's naturally occurring within the flame. And we ended up having such a nice movie that is converting initial natural luminosity or soot luminosity, hot soot luminosity movie into vector movie. So that's showing the vectors resembling the flame development and the flame structure. So instead of telling that, hey, flame is distributed here and flowing around, we can now say that, okay, there are flame that's going into specific direction, as it's a quantitative information that's obtained. For example, if you have ignition assistant plug presented within the flame, then definitely the vector is flowing around it. There's a flow that's winding around the rigid body that's clearly visible. And having this quantitative information is also giving us an opportunity to extract turbulence out of it. So we can run a Reynolds decomposition by applying spatial filtering for individual cycle of this. And we also have 100 cycles, so ensemble averaging is possible. Then we can extract the turbulence out of it. So how much of turbulence is included, we can estimate that by just running this FIV, flame image velocimetry diagnostics. Okay, that's a typical engine operation. You will hear lovely engine sound. Engine is running at 1200 RPM. High-speed camera is running. We have an image booster to make sure that the sensitivity is guaranteed. Time to time, we visualize liquid spray even before the combustion happens. Because of that, you see this green light. It's a green LED, not laser, illuminating the inside the cylinder, specifically for the spray visualization. And after we run the engine to take high-speed images like this. So that's the center of the combustion chamber where we have only 2 nozzles holes are open. Originally, this is injector with 7 holes. We laser welded 5, leaving only 2. Selected condition, and then we get to vary this jet combination by to change the jet-to-jet variation, jet-to-jet interaction strength. So that angle can be varied by changing the jet arrangement. For this, we have a jet 1 and jet 2. Jet 2 is going very close to the ignition system plug that's positioned right there at the 12 o'clock location. And we get to observe this hot soot luminosity movies and signals very strong. And when we run the ignition assistant plug added on top, as expected, of course, the ignition starts earlier, and the flame strength, the signal strength that we're getting from this hot natural combustion luminosity or hot soot luminosity increases. And then we ran this flame image velocimeter that I mentioned earlier, that as we extract the vectors, repeated message that definitely the initial flame development happens earlier as we have ignition assistant plug, suggesting that the control of combustion would be much better. Ignition is enhanced, so the combustion is enhanced for the benefit of operating this low reactivity fuel. But this particular condition, we used the fuel that comes with the cetane number only 30, kerosene-based fuel. So it was much needed energy boost from the ignition assistant plug that we needed to operate it together with the auto ignition potential that the fuel itself has. Then out of this flow vector information, out of 100 cycles, we extracted the bulk flow magnitude as well as turbulence. Both have a meters per second unit. So for the direct comparison, for the plug off and the plug on condition, and we compare bulk flow magnitude actually enhances in some area, particularly for the jet head wall jet head where the ignition assistant plug was located very close by. And for the turbulence also, we enjoy this enhancement of overall turbulence, as well as a specific region where this jet 2, the wall jet head has much enhanced turbulence that's observed from the FIV analysis. So from this, flame image velocimetry analysis, we could extract this turbulence or bulk flow magnitude value as a quantitative information, can confirm that when we have this ignition energy added to the engine through the ignition assistant plug, then we can enjoy the enhanced turbulence and enhanced bulk flow, which will explain the enhanced ignition and combustion that's observed from the engine performance test and all. So there are a lot of exciting diagnostics we can perform to the diesel engine. So it will last much longer than anyone else expected. And towards the final topic, I have hydrogen. The initial idea was originated from the government who is governing my university, the New South Wales government. They thought that we can actually develop the hydrogen production technology and storage technology that can revolutionize the world. So the idea was that in Australia, where the population is very low, but then the land is large, like China or United States or Canada, Brazil. We use abundant solar and renewable energy, wind energy, solar energy, and then any leftover that wouldn't be used during the peak hour that could be used to run electrolyzer operation for the separation of water into, of course, hydrogen and oxygen. And hydrogen that would be processed together with the nitrogen to generate actually ammonia. And then ammonia will be shipped out to other countries where the energy demand is really high, like Japan, Korea, and China. That was the original idea. The development stage at the moment is actually to the level that the hydrogen production is fully capable in Australia for renewable hydrogen production, and liquefied hydrogen has been shipped in between Kobe, Japan, and Melbourne, Australia. The port-to-port, the shipping was successfully done earlier this year, was it? I think last year. Now, that liquefied hydrogen, the Kawasaki Heavy Industry ship was operated with the liquefied hydrogen, so it was shipped all the way to Australia, and the renewable hydrogen produced in Australia was filling in the container, and they traveled back to Japan. Interestingly, there were a lot of news articles about the boil off gas, how much it was generated, safety concerns and all around, but all those issues were managed perfectly well, and there's one nicely demonstrated case that the shipping of hydrogen even across this long distance is very possible and feasible. So the opportunity is then, okay, this is a larger scale ship that is propelled by diesel engine. This particular one comes with a two-stroke diesel engine running on a heavy oil. What if we utilize some of this hydrogen, maybe those boil-off gas, to propel this together with the existing diesel engine? Wouldn't it be a great idea? And it's not just for the marine engine, but pretty much in any size of diesel engine or petrol engine could operate hydrogen as a fuel. I am old enough to remember the first wave of hydrogen that Ford was investing in, Mazda, part of a Ford at the time, investing in, and also BMW demonstrating their lovely Hydrogen 7 vehicle in Mini Airport. All this hydrogen engine technology development was a big buzzword in early 2000. But then, as I mentioned this, a lot of senior professors, to me, they also mentioned there was a big boom in late 70s around the hydrogen. So maybe that's a second wave. But for me, it's a second and the current wave that we're looking at with a big excitement that Toyota has developed this Toyota Corolla race car that implements a very high pressure direct hydrogen injection into their petrol engine. And there are many companies who are investing into some construction equipment companies, some retrofitting potential, the heavy-duty diesel engine manufacturers and marine engine manufacturers, very large-scale engine manufacturers are all committed to introduce new hydrogen engines. But then when you look at the details, then there are a range of technologies, not just a single hydrogen engine technology, but some of them are implementing high-pressure SI engine. Some of them are low-pressure direct injection SI engine. Some of them are simple substitution of intake air with a fraction of hydrogen. That's port injection, or even intake port, intake manifold supply of hydrogen into. Some engine manufacturers are introducing the integrated system where the single injector can do gaseous hydrogen injection and diesel pilot injection just from the one single injector. There are a lot of technologies being implemented. So as a brief introduction of hydrogen engine technology, I picked up some of the most advanced technologies of today, and it has to be divided into two. One is for passenger car, the other is more of a large bore heavy duty applications. So for passenger car applications, the most advanced research I actually found from the original injector manufacturers. The first one is Bosch, as always, that they have looked into the hydrogen jet formation when the 50 bar, this is a low pressure direct injection injector, was tested, there's a very interesting topic around it that the hydrogen must have longer penetration, otherwise it will be just attached to the wall thanks to its high diffusivity. So the Bosch researchers intentionally selected the nozzle configuration that can drive the hydrogen jet all the way down without being slowed down too quickly, or intentionally they selected the case that there is a ducted channel right at the exit of the nozzle tip, so that the flow of hydrogen is directed downwards more to maintain its original momentum. For bulk Warner, which is Delphi now, they are looking into also a very similar concept, 50 bar low pressure direct injection for passenger car SI engine applications. Their approach is different, that for better sealing of this hydrogen gas, they are using outward opening a needle, because that's a surface sealing, so it's performing much better compared to the original needle type multi-hole injector. And there are a very similar concept that if the hydrogen jet is developing without being directed in terms of the direction, then it might not perform better in terms of the distribution of hydrogen air mixture. So they intentionally select the jet that's directed more downwards to the piston. When the side mounted injector is applied to the engine, they want to have this direction so that the near TDC mixture distribution is a lot more homogeneous compared to the injector with no the fluid directing medium into it. This is for passenger car where the high pressure pump addition would be costly, so it would be very challenging. Also, the space will be quite limited. So the idea here is there will be a high pressure storage tank on board, and they will just use the pressure regulator to reduce the injection pressure down to 50 bar, and can use it without having additional pumping system. But then for heavy duty applications, we don't have much, say, the cost limitation restriction is not really high like passenger cars, and there are lots of space that's available within even a vehicle. So their application is more towards high pressure. For heavy duty application, there's an SI engine version and CI engine version. SI engine is more towards the hydrogen main fuel injection, or some of them are actually using pot injection, making very lean hydrogen air homogeneous lean mixture. And the ignition source is hydrogen, but then that's ignited by spark plug, and the flame is coming out of the small hole. So it's a turbulent jet igniter. Turbulent jet ignition is happening within this lean main hydrogen fuel mixture. That's the approach that's run by some of the manufacturers. Another approach is converting existing diesel engine into hydrogen engine, that you have integrated injector where the hydrogen jet is coming out from multi-hull, and in between you have a small diesel needle that's within the part of the one integrated injector, and that diesel pilot flame is generated due to simple fuel coming out from the diesel, and can serve as an ignition source for these hydrogen jets. So it's not compression ignition anymore. Compression ignition happens only for the pilot fuel, but then that's causing the ignition of the hydrogen mixture. Multi-hydrogen jet are ignited through the control of diesel pilot flame. That's the approach. For me, that's most advanced version of it, maintaining high efficiency of engine while enjoying this significantly reduce the CO2 emissions from the diesel engine. So UNSW's approach has been similar to those. Diesel hydrogen main fuel and diesel pilot ignition approach, but in a different way, that we maintain the existing diesel injector as it is, but then adding additional hydrogen injector as a separate to it. So it's a two injector operation. The idea behind it wasn't just back of the envelope calculation or whiteboard concept drawing, but our long time research on the hydrogen jet behavior. So we have in the laboratory a high pressure constant volume combustion chamber. something similar to Dr. retired now, Dennis Sieber's constant volume chamber back at Sandia National Laboratory. I personally did my postdoctoral research with Lyle Pickett, who was at the time operating Dennis Sieber's designed high pressure combustion chamber. Now he's very happy with constant flow chamber that he created himself. What a fantastic lab that he has there. Then we here at UNSW, we kind of mimic the design of Dennis Sieber's chamber. We maintain that capability in the laboratory. There, we injected hydrogen at very high pressure, which is 200 bar, 20 megapascal of hydrogen jet injection, and small amount of diesel that's going in. Before we implement this reaction case, we did a lot of research on hydrogen jet itself to fully understand what's going to happen for this high pressure and hydrogen injection. From this non-reacting jet study, we found this exciting battle shock structure from high pressure injection, confirmed that this high pressure 200 bar injection is giving out the choked flow for the hydrogen, which is a great benefit because you can just simply control the back pressure and then supply pressure and the flow rate control will be linearly corresponding to the control of the supply pressure. Excellent opportunity for us. All these things have been confirmed. And of course, we thought that, hey, we can just auto-ignite hydrogen with no additional means because we can control the environment in an engine. But then it turned out that the hydrogen auto-ignition itself is quite random regarding the spatial location of the ignition source. So all the jet-to-jet variations and this combustion cycle-to-cycle variations would lead up to an acceptable level of cyclic variations. That was confirmed. So definitely when you run hydrogen, you need either spark plug as an additional ignition source or diesel flame as an ignition source, just like it here in this case that we applied. So our approach here was to maintain the high repeatability, low cyclic variation, good combustion stability. We inject hydrogen at high pressure, but then there is always small amount of diesel as a pilot that's going in, just like that. And once the reaction, auto-ignition happens within the diesel flame, then the reaction zone spreads out and engulfing this developing hydrogen jet head very quickly and releasing large amount of heat that's good enough to operate the engine. And we didn't stop there. We applied that to one of the existing engines that we had, one of the existing diesel engines that we had, and had a engine dynamometer testing, which I'll just briefly introduce later on. So for this hydrogen jet operation, one's idea would be, hey, if you can do this lovely Schrieden imaging showing off the shadow of gas jet hydrogen 200 bar jet, why don't you put the diesel flame, this is a normal heptane by the way, let it auto-ignite and see what happens. So we looked into the very long dwell operation in between hydrogen and diesel injection. We intentionally maintained long delay, and then we ended up having very small amount of heat that's released from this, so wasn't really happy with it. We moved on to the reduced gap such that the hydrogen jet is right there, and then we put the diesel flame into, see how this hydrogen jet is turning into reacting hydrogen jet so quickly, maintaining the heat rate profile that's looking now just like a typical diesel engine that has a premixed burn and a bit of a mixing control burn following the premixed burn phase of combustion. Excited, and then we even shortened that in a way the diesel flame and hydrogen jet development occurs almost at the same time. So the diesel flame going in, and at the time the hydrogen jet reaches to the expected the auto ignition point, the reaction start off quickly, and then there is an extended, as expected, mixing controlled combustion phase. So we are controlling this premix burn and diffusion flame mode effectively by just controlling the sequence and the dwell time between hydrogen direct injection and diesel direct injection. And what many of are interested in at the moment is this, that you put the diesel flame in first, let it self-ignite, auto-ignite, and then hydrogen jet is injected into, which means that we are using only the diffusion flame, mixing controlled combustion or the hydrogen. That would be translated into engine test condition as the injection timing control. So this is implementation of what we learned from the optical diagnostics, the constant volume chamber. In an engine, we set the injection timing of hydrogen, direct injection, all the way from the bottom dead center, 180 before top dead center, to 60 before top dead center. And it all turns out that this is more or less a premixed combustion mode that we noticed from earlier flame case, that largely the heat is released from the premixed burn, and that was actually limiting the proportion of hydrogen that can be operating in the engine. For example, this TDC operation, we could only go up to 30% diesel, down to 30% diesel, and 70% of energy, total energy was supplied by hydrogen. So it's a 70-30 operation from hydrogen as a main fuel and 30% diesel fuel. But then we, of course, wanted to increase the hydrogen energy fraction as much as it can. That wasn't possible, as if we increase the hydrogen fraction further, then this start to struggle with a massive knocking, meaning that the hydrogen premixed combustion has a clear limitation, and that counter explains the why the pot injection of hydrogen or the intake manifold injection of hydrogen wouldn't actually give us an ultimate answer to the dual fuel combustion operation, because essentially it's a premixed burn of hydrogen would really struggle and are limited by the knocking, massive knocking condition, engine damaging knocking kind of condition. So we then delayed injection timing much to the later, and that's where we start to see the behavior that's looking like a diffusion flame or mixing controlled combustion flame, combustion control behavior. And with that, then we could achieve up to 90% hydrogen operation, meaning that to the total 100% energy, 90% of energy was supplied by hydrogen, only 10% from diesel. Couldn't reduce further down in this case because the diesel injector duration was limited. We couldn't actually reduce that diesel injection duration further down. For that, we would increase the load so that the injection duration is increased and total amount would be increased. But for this, we were still very happy with this 90% hydrogen operation and only 10% diesel mass operation. This is more towards diffusion flame combustion, and especially when the hydrogen injection was done at TDC, second TDC is at the end of compression stroke, then we ended up having the almost 100% diffusion combustion, mixing controlled combustion. That crossover point in between premixed burn and mixing controlled combustion could be identified by just looking at the combustion phasing measurement. The CA50 is a crank angle position where you get 50% of the total heat release observed, and that to the hydrogen injection timing, we observe, for example, 90% hydrogen operation. It has to be somewhere around 30% hydrogen, 30 crank angle bTDC, so just 30 crank angles before top dead center. It has to be, that's where the combustion phasing is still maintained while the mode switching happens in between. So if it's earlier than that 30, then it's more or less a premixed combustion. If it's later than that, it's more towards the mixing controlled combustion. What's the benefit of the controlling that? Control of efficiency and NOx. So the efficiency that we can achieve out of this is impressive. When you do premixed hydrogen, 90% energy supplied, then we can hit, well, this is an indicated efficiency, net indicated efficiency of 57.5%, which in theoretical comparison, it's higher than even the fuel cell system. Pretty excited, but then by looking at the NOx chart, we start to be, okay, depressed almost that, okay, what do we do with this massive NOx amount? But then by looking at the CO2 emissions that we're getting, we were excited again that, hey, if we control the hydrogen injection timing, depending on the engine operating condition, to the level that it is matching the highly efficient diesel operation, and so the NOx is also leveling with the baseline diesel operation. In this particular example, you will set 30 crank angle before TDC as a hydrogen injection timing, then that's where we get the almost identical engine efficiency to the baseline diesel operation and the NOx level, while we are simply enjoying the CO2 reduction. That's almost 71% reduction just from the hydrogen operation in an existing diesel engine, retrofitted existing diesel engine. So there is a great excitement about it. So the future direction for this hydrogen engine application, we are continuing this fundamental hydrogen jet research, but at the same time, we are scaling up our operation. The initial engine was only 83 millimeter bores, so just a half liter per cylinder. The new engine that we've just installed and in operation nicely has 1 liter per cylinder, 100 millimeter bore. So that's directly suitable for many of the power generators available out in the Australian mining sites. And not only the dynamometer testing that we're doing, but also we continue our optical engine diagnostics. So there are many exciting diagnostics lining up for the hydrogen mixture making and then also the dual fuel combustion operation. So the research will continue. So to sum up just briefly, I've introduced as ingredient for the future internal combustion engine. The gasoline engine will survive much longer than my lifetime and many of yours. That requires further improvement in efficiency, meaning that we have ample lots of opportunity by looking into its flow structure, its turbulence distribution, and how the efficiency improvement can be achieved out of this existing petrol engine, gasoline engine. And for diesel application, we might be diverted into more of a detoured into other application areas for now. Who knows that you might come back to passenger car application. Until then, we'll find other opportunities like backup power generators, this unmanned aerial vehicle where the diesel engines are still actively used, and where the demand is clear for the alternative fuel usage or specific type of fuel that has to be refined for the utilization in the diesel engine. And to that, we continue to develop exciting new diagnostics to provide enhanced fundamental knowledge. And for hydrogen, we've achieved this 90% hydrogen high pressure direct injection by energy and 10% diesel operation, which achieves very impressive 70% CO2 reduction. So getting a lot of attention from everyone pretty much, not only research, but also investors, also public, which we really enjoy and appreciate. There is a great opportunity out of here that as you're controlling the hydrogen injection timing and the ways that we're delivering hydrogen directly into the cylinder, there's a great potential that you can optimize the efficiency and NOx altogether while enjoying the significantly reduced CO2 emissions. All right, so the last slide to acknowledge my team. During the pandemic, we survived through very okay. Looking back, it looks all great. In between, we had a terrible times, but then as we get together to celebrate the successful conclusion of each year, we were really happy with it all. So I'd like to acknowledge everyone's great contribution to our continued research effort. Dr. Dongcheng Kim and Dr. Mark Jai are leading researcher within our team, contributing greatly to everywhere, including all those areas that have presented today. Graduate students, Xinyu Liu, Jinxin Yang, Chris Zhao, Hao Xin, and Qinghua Zhang are very active researchers within the team. Alistair Heaton will join us very soon in the following term. And Luvin Chiang is a current undergraduate honors student, if you're familiar with that system, and British system, I think. And Luke Jackson is another student joining in the next term. I'd like to acknowledge their great contribution to the research. If there's any questions about the talk that's given, live questions today, happy to address them. Otherwise, like I mentioned earlier, please try to reach me out to ask questions. Thank you.